could be measured in AMUs, or you could talk about the mass of a mole of molecules, and then it's the molecular mass.
Oh, so molecular mass is just a mole of molecules.
Yeah, it's the mass of a mole of molecules, so a whole bunch of them. But it's still a valid, if you're comparing two different molar masses, it's the same as comparing the masses of singles molecules,
Okay.
if you're comparing.
And AMU is just in grams.
Well, so AMU is not is its own measurement. It's there is a conversion in grams.
I actually wasn't reading that. I just saw the
But
parallel and it made sense to me.
AMU is chosen in a way that it's equivalent, like it uses the same number as grams per mole. So like
Right.
a carbon atom weighs on average 12.1 AMUs, but
Right.
a mole of carbon weighs 12.1 grams.
Right,
Yeah.
okay, I understand.
So it's related by Avogadro's number. That's the conversion.
Right.
Yeah.
Wait, what? If they're the same number, how are they related like that? I don't understand how you can multiply it by.
Well, one carbon atom
Yeah.
is 12.01 AMUs. If I've got a mole of them, that means I've got 6.022 times 10 to the 23rd. So I'm going to multiply that.
Oh, so you divide that number by Avogadro's number, and then it's the mass in grams
Yes.
of one atom.
Yes, yes,
Right,
yes,
right.
yes.
I understand now.
Yeah, they don't normally, the conversion is not normally written as Avogadro's number. It's written as the inverse of Avogadro's number, which is something times 10 minus 24.
Yeah.
Yeah.
Fair enough, fair enough.
I might be getting 223 in the fall, FYI. So if you're waiting till the fall to take it, I might be teaching it. If you're taking it in the summer, then who knows? I'm not teaching in the summer.
It's the absolute worst options ever to take it in the summer.
Yeah?
Yeah, it lasts until 10 o'clock at night at
Uh.
Owl Creek. So,
You're going to do it? No?
I don't know, because I don't think I can take both Chem and Chem 3 at the same time. If I took it in the fall, I'd have to do that.
Oh, yeah. Okay. Yeah, because you want to be in sequence, I guess. Yeah. Okay.
I'm actually looking at Clackamas to see if I can take some classes, but take it there instead.
Mhm.
And at
I mean, it would
PSU.
just be heavier.
I know there are people that teach here and at Mount Hood Community College. So, I mean, it's a long drive, but it's not impossible.
We only really like
I don't know what they offer there.
What'd you say?
If you do it online, that would be ideal.
There's also a community college on the coast.
Yeah.
I forgot what it's called though. We have relationships with them.
That makes sense. Yeah.
What do you think?
Why didn't you
As soon as there's a just give me a question.
Like in parallel operation, oh, our energies there are also like they're not trying to our energy.
I wrote down just H2 and understood that. No, there's 3, 2, H2O.
Okay. All right. Maybe you have enough time to get through some of it, most of it. If not, don't worry about it. We'll talk. But I kind of want to hear what people have to say about 1 and 2. So xenon has a higher boiling point than neon because xenon atoms are heavier than neon atoms. Would you say that's true or false?
True.
So why true?
Because it needs more energy, more kinetic energy for escape into gaseous form?
That's actually a good answer. Yeah, the heavier it is, the more energy you need to accelerate it. Make it move. I think, though, boiling. Well, yeah, I guess that's true. It's not the main reason, though. So somebody said no. Yeah.
Yeah, I know because we said there's like a correlation between
Mhm.
larger like molecular mass and higher boiling points, but it wasn't because they were heavier. It was just because the more atoms, the more molecular forces, the more energy it takes to break them up. Right?
Yes. But why? Why higher? Like, so what about the higher molecular mass? What about it makes it have more IMFs? Like, so let's talk about between helium, or was it neon and xenon? Is it neon? Yeah. Neon has, if you do the shell model, it's got a +10 nucleus, and it's got 2 shells, right? It's got your 2 electrons here, and you got your 8 electrons here. That's not enough. 8. Whereas xenon, I'm not going to draw everything, but xenon has 54 protons at the nucleus, and it's got 5 shells. 1, 2, 3, 4, 5. And that outer shell has a ton of electrons in it. But the difference here is these electrons, if you calculate a core charge, they're feeling a +8 core charge. I believe if you calculate the core charge here, technically you'll calculate a +8 core charge. But regardless of the identical core charge, these electrons are closer. These electrons are much further away from the nucleus. And so they're less attracted. I mean, we learned in 221 that xenon has a lower ionization energy. As you go down the periodic table, things get lower ionization energy. So it is easier to remove the electron on xenon. We're not talking about removing them. We're talking about, in this case, distorting the electron cloud. Being able to have an outside influence, push the electron to one side or pull it to one side. So if a dipole moment comes close to this xenon atom, these electrons, if the dipole is the negative side is here, these electrons will move to that side temporarily and create a temporary dipole. Whereas these electrons are less likely to do it. They are less polarizable. So that's the key here, is the polarizability. And that correlates with molar mass. So the higher your molar mass, the more likely you're going to have a polarizable atom. The bigger the cloud the electrons are going to be. Now, there's not just polarizability. There's, when we saw the tables before, the alkanes and the ketones, as you increase those molar masses, the boiling points went up as well. But you weren't going to higher, more polarizable atoms. You were just adding more carbons. So the other way that you can increase boiling point from molecular weight is just by the sheer number of electrons involved. So a short chain can only create induced dipole moments along the length of that short chain. Whereas if you have a long chain, you have the potential to induce a dipole moment anywhere on that chain. And the more chances you give a molecule to create that induced dipole moment, the more likely it's going to happen. So it's all probability. So more surface area, longer chains are going to have more likely to, or are going to make more dispersion forces, and so have a higher boiling point for that reason. So yeah, I like the idea of more kinetic energy required, but it's not the main reason. But yeah. And then 2, forces between water molecules are attractive and not repulsive. True or false?
Well, it depends.
It depends, yeah, because if you scroll down, there's one right here, repulsive. So it's not super simple. Yes, there is a dipole in 2 water molecules. They each have a dipole. They have a positive and negative side. But just like a bar magnet, if you put the 2 poles together, they repel. And water will do the same thing if they're oriented the wrong way. And that orientation is important. We're going to look at it a little bit in the next coming slides. But organic chemistry, that is a big deal. Orientation of molecules is a major, major component of understanding reactions in organic chemistry. So honestly, it's the visual, the 3D aspect of organic and the memorization make it a little bit tough for some people. That's why it gets tougher than what, this is more math, more conceptual. So that's why people have a hard time with organic. They did all this Gen Chem and they're like, yeah, some of it helps me, but it's nothing like Gen Chem. So anyway, just want to warn you. It's fun. I liked it. Not enough to do it like full time, but it was fun. In which system is the model? So I think my questions are slightly different than yours, but I think they correlate a little bit. Which system has the repulsive? Which system is weakest? Which two have the strongest interactions? So, I mean, I'll go back to this one. Here you've got the weakest. Here you've got the strongest. The weakest is your two neons because it's the least polarizable atom. There's no dipole moment whatsoever. These are the strongest interactions. And that's because they're not really IMFs. They're bonds. This is an ionic bond. Ionic bonds are somewhat similar to intermolecular forces because they both involve charges or attractions between charges. But ionic bonds occur between full charges, a -1, a +1, +2, -2, whatever. These are all partial charge attractions, okay? A fraction, a small fraction usually. And this is a covalent bond. This is, it's an intramolecular force, not an intermolecular force. So these are so much higher, you can tell. What else do we have here? Which system in the model would you expect to have the lowest boiling point? Where would you expect to have the highest? So boiling point, this is a physical property. IMFs are going to affect physical properties, boiling points. That's going to have the lowest boiling point because it has the weakest IMFs. Ignore these. These, again, are not, well, this is a special case. But this one is definitely not an intermolecular force. This kind of is, even though it's an ionic bond, because your smallest particle in an ionic compound is the ion. And so there's a particle, we can separate them. Technically, that'll have the highest boiling point. It's very, very difficult to turn table salt into a gas. But if we, after that, it's the water, right? So this is, you don't even consider this because this is an intramolecular force. You're not going to break the bond. If you do, it's not a physical change anymore. It's a chemical change. But for an ionic compound, this sits kind of in the, like I said, it's halfway between a real bond and kind of like an intermolecular force as well, because we can separate these ions and still call it, an ion. All right. We talked about 4, or at least on mine is 4. Why do you think more energy is required to separate two xenons? So it's all about the polarizability of the electrons. Those outer electrons on xenon are a lot easier to distort. They are more loosely held. Why do you think that the energy is required to separate two water molecules in the anti-parallel configuration, but in the parallel configuration, water molecules repel each other? So here's what we're talking about. We need energy to separate these because that's the energy required. These are repulsive. If you draw the dipole moment for these, it should be kind of clear what's happening. So for the anti-parallel, all right, I will draw the water molecule behind first for this picture here. It's got a dipole moment going that direction, right? The arrow points to the partial negative side. It's pointing towards the most electronegative element, which is the oxygen. And the tail end is towards the hydrogens. Above that is this molecule here on top, and it's going the opposite direction. So there's a dipole moment going that way. And if you think about this, negative is next to positive, negative is next to positive. That's fine, opposites attract. And that's why there is an attraction. But for the parallel poles, it's literally, they're both going in the same direction. And That's no good. You're having the two positives near each other, the two negatives near each other, they will repel each other. The next question on mine, what about head to tail versus anti-parallel and parallel? So head to tail, why is this energy so much higher than this one? So if you draw, I'm going to draw the dipole moments for these two. So first, the one on the left kind of goes in this direction. Again, we're pointing the arrow towards the most electronegative element. And then the other one, it's kind of coming out towards us a little bit, but I'll just draw it like up like that. There it is. So this is higher energy or lower energy. It takes more energy to break that connection than this one up here. And if you think about it, you have a negative next to a positive, and that's it. That's exactly what you should expect for an attraction. So why is this one lower? Well, it probably is because this negative is too close to this negative. It's too compact, right? It's this, even though they are kind of oriented in a okay way, these two oxygens are still way too close to each other. I mean, you can see it in the drawing. They're too close. The hydrogen sides of the molecules are also too close to each other. So there is an attraction there, but it's a weaker attraction. This is preferred. And all of this goes into why snowflakes make the patterns they make when they form. It's because the water molecules have to orient themselves in a certain way so that when they are packed together in a solid, the positive end of one is next to the negative end of another, and not vice versa. Or not the opposite, I should say, not negative to negative. And so with snowflakes, you get these six-sided shapes often, and I'll show you a little bit how that might happen. What's that?
They can manufacture snowflakes like identically.
Can they? I haven't seen. Oh, that's cool.
Yeah, they change the humidity in the temperature.
Huh. Interesting. Okay. All right, I think we're here still. Okay. So we've covered this. This is, again, intramolecular forces. Again, note the energies involved are pretty large. Metal slightly lower than everything else, but still high. And here's the same thing. So let's focus on the intermolecular forces. Annoyingly, I'm going to say this, we get these slides piecemeal, some from different books, and some are just made up, some from the internet. Every book will kind of categorize the intermolecular forces a slightly different way, or emphasize the categorization, I guess, a little bit different way. We're going to just use the umbrella term intermolecular forces, but there are a group of intermolecular forces called the van der Waals forces, which usually is dipole-dipole forces and London forces, sometimes including hydrogen bonding. We'll get to what hydrogen bonding is, sometimes not. But we're also going to talk about other intermolecular forces like ion dipole. I think we looked at that already. So the categorization is a little bit confusing, I will agree. But just put them all under the umbrella intermolecular forces, and then we'll be fine with that. So here we go. These are the IMFs. We've covered dipole-dipole forces. We've started talking about London forces or London dispersion forces, or induced dipole forces. They're all the same thing. And they're the weakest. So when you have nonpolar molecules, something that doesn't make a dipole, how would it ever make a liquid? How would it ever make a solid? You get distortions of that cloud of electrons, and you will get a temporary dipole moment. So we talked about this. So two helium atoms. They're completely neutral. They have 2 electrons each, 2 protons in the nucleus, maybe a couple neutrons as well. And when one coincidentally gets near another one, maybe the electrons for one helium is coincidentally on one side, and it causes the other helium's electrons to be repelled away. And you'll get this temporary dipole moment where you've got a negative side here, a positive side here, and an equivalent positive and negative side here. There is a temporary attraction before the cloud kind of resets, and it's not going to. Their electrons are not going to stay where they are. But there's plenty of these temporary interactions. And remember, we're dealing with really large numbers of atoms. So even if it occurs not super often, there are so many atoms that it does occur a lot. And this is how things become solids and liquids, even if they have no dipole moment. Iodine, I2, is a nonpolar molecule, right? The two electronegativities are exactly the same. It's nonpolar, but it's a solid at room temperature. And the reason it's a solid is because iodine is super polarizable. These electron clouds are easily distortable, and the London dispersion forces are strong enough to keep it in solid form at room temperature. So even though they are the weakest force, they can be fairly strong. All right, so here are two chlorine atoms. We looked at this already. They get closer together. They can induce a dipole moment in each other, which will create a temporary attraction. And this just fluctuates throughout a liquid. For helium, that's the worst, right? Helium is probably the least polarizable atom on the periodic table. So if you're going to make attractions with two heliums, the attraction is super weak. It's on the order of 0.1 joules per mole. Just to give you an idea, that is 10 million times smaller than covalent bonds are. So tiny, tiny attractions. And I'm going to skip this because we talked about this. Some of these slides are out of order. I think we're going to see, hold on a second. Yeah, so helium, there it is. It turns into a liquid at 4 Kelvin, right? You've got to cool it down to 4 Kelvin, which is, 0 is the lowest you can get, before it'll turn into a liquid. Yeah.
So in this picture, we see both of these with their dipole moment momentarily.
Uh-huh.
Does all of the atoms in a structure or in a liquid or whatever, do they all sort of pulse at the same time, or does it happen sort of one area then now?
I believe it's chaotic.
Yeah.
Like, I don't think it's concerted. Otherwise, you would get weird stuff would happen in the macro scale.
Yeah, okay, that's fair enough.
Yeah, I think it's chaotic enough that overall it looks neutral. Nothing seems to be happening. Yeah. Okay. Yeah. Oh, that's not what I want. There we go. All right, so we've seen this similar, but now it's in graph form. These are the boiling points for the different alkanes plotted against their molecular weights. And it's pretty clear that as you increase the number of carbons, as the molecular weight goes up, the boiling point increases. So why does that happen? It's not the molecular weight, it's the fact that you've just got more places for an instantaneous dipole to occur along a larger molecule. All right? So the surface area is going to be a key part of why something is more polarizable than another thing. So the more surface area you have, you're going to see stronger dispersion forces. So how do we prove that? Well, we'll get to that in a second. So we'll go over dipole-dipole forces very quickly. It occurs when you have a dipole moment. So anything that is not symmetrical. So methane, where you have a hydrogen here, is completely symmetrical. It has no dipole moment. You've got a chlorine here instead. It's now asymmetrical. It's got a dipole moment. These have stronger IMFs than dispersion forces do. But you got to remember that even though they are stronger, it only occurs in one spot on this molecule. Like if I had a long chain of carbon and only a chlorine at the end, that end part is the only place where you'd have the strong IMFs. So even though it is a stronger force, it's only occurring at that one spot on the molecule. Okay. We've talked about this. Ammonia and water mix really, really well together because they both have these strong dipole moments, and they can interact with each other really, really well. I don't know what else to say about that. We've seen this already. This is a chart that shows how as you make the dipole moment stronger, you are increasing the boiling point. And again, it doesn't look like it's much, but this is going down to 0. So the scale is humongous. Yeah, there's a big difference in boiling point here.
What's room temperature in Kelvin, by the way?
298.
Oh.
Depends on what you define room temperature. 25 degrees C, which is kind of warm,
Yeah.
is 298 Kelvin. Yeah. Okay, we've talked about this. I'm going to skip that. Not a big fan of this question. So now we're going to get to the last category of IMFs. And so we've kind of looked at this side of this graph, and we've explained as you change carbon out for silicon, for germanium, for tin, the boiling points go up because you're putting in a heavier atom, an atom that is more polarizable. So that makes sense, and it occurs for any of the groups. But what doesn't make sense is why these are up here. Because, well, methane follows the trend as you go to lower periods, the boiling point goes down. But if we looked at water, H2O, so after H2S, we would expect water to go down just like methane goes down. But it doesn't. It goes way up in boiling point. So the same thing happens with ammonia. The same thing happens with HF, but not with methane. So these three elements, nitrogen, fluorine, and oxygen, there's something special going on with them. They are bucking the trend in terms of what we'd expect for a boiling point, for a compound made with those elements. There we go. So why is that? Well, we're going to turn to electronegativity again. We examine the difference in electronegativity between an oxygen and a hydrogen, a nitrogen and a hydrogen, a fluorine and a hydrogen, and all the others with hydrogen. Carbon hydrogen, the difference is about 0.2, depending on the scale you're looking at, depending on the electronegativity table, which is tiny. That's why we think of carbon-hydrogen bonds as fairly nonpolar. Hydrogen silicon is, not very big either. Hydrogen chlorine is a little bit bigger, but still not great. When you get to nitrogen, you might think, well, 0.8 is not that much different. But you could see from the graph that something about nitrogen makes it different. And so we're going to include it on this side of this line, dividing line. And HO 1.3, HF 1.9, these are huge differences in electronegativity. So it's basically the electronegativity of nitrogen, oxygen, and fluorine make them a little bit special when it comes to making these dipole moments. And so instead of calling the interaction between molecules that have these HF or HO or HN bonds, instead of calling them simple dipole-dipole interactions, which they are dipole-dipole interactions, but we're going to categorize them as a special kind of interaction, and that interaction is called a hydrogen bond. And it sounds very confusing because it's not a bond that we think of, right? It's an unfortunate term that we've come up with, but that's stuck. And this is basically the dipole-dipole interaction between two atoms, but only when an HF bond, an OH bond, or an NH bond is involved. So here is HF, the molecule, and it's a polar bond. It's got a dipole moment. This fluorine is partially negative. It'll interact with the partial positive of another HF molecule. But this interaction is so strong, much stronger than regular dipole-dipole interactions, that we call it a hydrogen bond. Okay? So that is an intermolecular force called the hydrogen bond.
And that only stands for fluorine, oxygen, and nitrogen?
Yes, with hydrogen.
With hydrogen.
So I'll clarify a little bit more even. So here are some examples. And let me move that out of the way because it's in the way. So water. And I've been lying to you because I started calling water dipole-dipole interactions. And they are. but it's a special kind. Water, since it has an OH bond in it, it's got an OH covalent bond in it, water will do hydrogen bonding with neighboring waters. So that special dipole-dipole interaction, that's what we've been calling it. This one's not just a dipole-dipole interaction, it's a hydrogen bond. So as long as there is a OH, NH, or FH covalent bond within the molecule, that molecule will do hydrogen bonding with other molecules. So here's ammonia. It's got an NH bond in it, and so it'll do hydrogen bonding with neighboring ammonias. The hydrogen is always the partial positive, and the hydrogen is always going to be attracted to some more electronegative element. Okay?
So the lone pair there, that obviously, how does that affect that? Because I feel like the two lone electrons would still have a negative charge.
So this is a slightly different way of thinking about it, honestly. If you start looking at lone pairs, and that's more the organic way of thinking about how things interact, is looking at lone pair electrons. But it's the fact that it is more electronegative means it's more likely to have the lone pairs on it in a molecule.
Yeah.
So like AF has 3 lone pairs. So it correlates with the same idea. So we are going to think yes, we should think in terms of electronegativity. Organic chemists will think more lone pairs. So it's the same idea though.
Fair enough.
What is the H always bonded to?
So for the intermolecular force, the hydrogen is always going to be attracted to a more electronegative element, because the hydrogen is always going to have the partial positive charge in these kinds of interactions. Here's some more examples. So HF is a funny one because the only time you'll see HF hydrogen bonding is with the molecule HF. That's it. There's no other scenario, and you'll see why in a little bit. But for HO and NH, it's like there's a multitude of scenarios. So here's ammonia interacting with water, interacting with another ammonia. These interactions between the molecules are all hydrogen bonds. Here's water with ethanol. And that does hydrogen bonding as well, because there's an OH in the ethanol, not to mention the OH in the water. By the way, if you're interested in distilling, like if you like making your own booze,
Yes.
when you have this water, alcohol, and other garbage mixture, and you're trying to separate out the ethanol, the attraction between water and ethanol is so strong that when you try to separate by difference in boiling points, ethanol has a lower boiling point than water. Even though the ethanol will boil first, it pulls water with it. So you can never get 100% pure ethanol. Like when you distill, you're always getting a little bit of water mixed in with the ethanol when you try to separate it out through distillation. This is a special case. Don't worry about it in this class, but it's called an azeotrope. When you get these things that should have separate boiling points, but when you mix them together, they have these variable boiling points now. So this hydrogen bonding occurs in a lot of places. So formic acid. What makes a thing an acid? It has this carboxylic acid group. It's got the C double bond O, and then the OH. And the fact that there's the OH in here means this thing can do hydrogen bonding. So how would it do hydrogen bonding? Well, it could do hydrogen bonding with the other OH, but this hydrogen could be attracted to the oxygen on the C double bond O as well. Like this partially positive hydrogen is attracted to anything that is more electronegative than it is. And so you'll get these things, these little dimers, they call them, 2 molecules kind of attracted to each other. This is salicylic acid. This is the precursor to aspirin. So if you take this, it'll have the same effect as aspirin, but since it's an acid, it'll upset your stomach a little bit more. So they convert it to something else to make it better. But this does internal hydrogen bonding. So the OH that's on this ring will be attracted to the C double bond O, the O, through hydrogen bonding. How do we know this? we can look at like how the bond stretches, and we can tell that it doesn't vibrate like other OHs. It's actually connected to that a little bit, so it changes how it stretches and it changes how it vibrates. So anyway, we know this. Here's 2 amino acids. And so, never mind hydrogen bonding with these OHs here. Of course it could, but you've got an NH that can hydrogen bond with the O over here. I mean, so the possibilities are limitless. And hydrogen bonding is how DNA base pairs, the nucleotides, zip together. So the 2 double helix of a DNA strand, they are held together with hydrogen bonding. The proteins that fold together to make these large shapes are folded together through hydrogen bonding mostly. So this is a big deal. Hydrogen bonding is probably the biggest deal there is. Without it, water wouldn't be water like as we know it. So think about it. Water is only 18 grams per mole. It's super, super light. It should be a gas at that molecular weight, but because it does hydrogen bonding, it is a liquid at room temperature. If that wasn't the case, life would be very different. So here is an example that I was going to bring up. Which one of these does not do hydrogen bonding? Hydrogen bonding, this is the intermolecular force that connects 2 molecules together, not the covalent bond of a hydrogen to something else. But
Yeah, so just to be clear, the reason the hydrogen is attracted is because of the dipole moment that it makes with the other atom.
So
The
the
nitrogen
OH,
oxygen
the oxygen is super electronegative, so the hydrogen picks up the partial positive charge. In that case.
And then that attracts to a different electron, which can create its own dipole moment through, what was that term used? Polarizability? Whereas it's innate.
It- So anything that is more electronegative, so I'll have to show you with an example, but yeah, anything that has a dipole moment in another molecule, anything that is an atom that is, so if you have an electronegative atom, generally it's probably going to have a dipole moment somewhere.
Yeah.
But so that hydrogen, that partially positive hydrogen, is going to look for other partial negatives to associate with, to be attracted to. Yeah. That attraction lowers the energy for everything. Okay. So we've got most voting for C, and that was it. So the reason C is it is because if you draw this thing out, CH3, CH2, F. That fluorine is not connected to another hydrogen. The requirements for hydrogen bonding to occur with other molecules is you need to have an FH bond, an OH bond, or an NH bond. And I do not have an FH bond. I've got an FC bond. So that's why I was saying that for fluorine, really the only molecule that does hydrogen bonding with fluorine is HF, because fluorine can only make one bond, and that's it. But for OH and NH, those are everywhere. So you'll see that more commonly. Okay? Okay. Let's do this together, because this is one where maybe that also doesn't. Or let me take a look at this real quick. Hold on, 12 to 18. I did this the other day, and I still can't remember what we did. Wait, this is 25. That's why it was weird. So we're going backwards here. So we did 25A, we're going back to 25. And yeah, okay. So this is Model 3 in CA25. I don't know what page it's on. I don't know if anybody. 66, thank you. So let's do this together. So again, these are basic questions. What is the difference between intramolecular bonds and intermolecular forces? Well, the big difference is the energies involved. Right? Intramolecular bonds lower the energy of the molecule a lot. To break them, you need to put in a lot of energy. Intermolecular forces don't require much energy to break. Another difference, intramolecular bonds affect the chemical properties of your molecules, whereas intermolecular forces only affect the physical properties of your molecules. Right? So if I make a new bond to a molecule, I'm making a new molecule, it's going to have different chemical properties. It's going to react differently. But intermolecular forces just affect things like boiling point, physical properties. All right. And then this is, again, very basic. Rank these in terms of regulative strength, hydrogen bonding, dipole-dipole interaction, induced dipole, which is another name for London dispersion forces. And the ranking is basically the opposite. So induced dipole is the weakest, then dipole-dipole, and then hydrogen bonding. Okay, so the next ones are kind of important, and I've tried to emphasize this when talking about them before, but alkanes, what type of intermolecular forces are present? So an alkane would be something like that. There are no dipole moments in there. It's a nonpolar molecule. So the only IMF present is London dispersion forces. And so the strongest IMF is the London dispersion force. That's it. For a ketone, which looks like that, there is a dipole moment, right? That's right there. And so this will do dipole-dipole interactions. It will also do London dispersion forces. Everything does the dispersion forces. Everything does. But the dominant force is the dipole-dipole. All right. That's not to say that it's the London dispersion forces is not important. We saw that when we looked at a series of ketones and we made the chain longer, the boiling point went up. So London dispersion forces are still relevant. Alcohols. What type of intermolecular force is present? Well, it's not dipole-dipole because it's the special kind. It's the hydrogen bonding. It's got an OH in it. So the fact that it has an internal OH bond means it does hydrogen bonding. But it also does London dispersion forces. Everything does them. And again, the strongest IMF in this case is the hydrogen bonding, not the London dispersion. So we talked about 17. I think this is one where your questions don't match up as well. What does the boiling point? Why does the boiling point of a type increase as the molecular weight increases? Well, you're just increasing the London dispersion forces. You're not adding a new dipole in there, so it's more London dispersion forces. And I guess let me skip 18. Yeah, we'll just skip that. That was just kind of explaining the difference between alkane, ketone, and alcohol, which we just did. Okay. So that's just a nice little review. So like this question, which one of these would you expect to have the highest boiling point? And I promise you, on an exam or a quiz, I will give you a choice, a set of choices that are easily distinguishable. There's not going to be any, I'm not sure. These are hard to compare. So they should be easily distinguishable. Because one of these slides in the future is going to be a little harder to do, but we'll talk about it. Okay, so we'll stop it there. We have votes for D. Excellent, you guys got it. So you zeroed in the OH. That one has an OH too, but that one has an OH. So hydrogen bonding, that's the strongest. This is an ether. It only does dipole-dipole. So this is why you have to know the functional groups. What does an ether look like? Remember that an ether has, here I'll draw out the whole thing. An ether has a tetrahedral geometry around that oxygen. And so it is bent, and I can't write my letters today. So it is bent, and if you do the dipole moments here, you've got a small one here, you've got a small one here, and these add together to create a dipole moment that goes that way. It's not very strong, though. Ethers do not have strong dipole moments. They are dipole moments, though. But that's weaker than hydrogen bonding, and this is nonpolar, London dispersion forces only. So when comparing the two hydrogen bonding, all right, I don't know why I'm explaining, you guys got it right, but it's got a longer chain, so more dispersion forces, just in case you were guessing. Okay, and we can verify this with boiling points. So yeah, it's pretty clear. Ethanol boils at a higher temperature than methanol does. Ethanol being that one, methanol up here. This is also known as grain alcohol. This is also known as wood alcohol. This one will kill you in large doses. This one will make you blind in small doses and kill you in large doses, of course. Everything is in moderation. Dosage is important. Some things kill you with low doses, so don't do those. Yes?
Just wondering if the difference in boiling point there is due to molecular weight, because they're both doing hydrogen bonding, right?
Oh, these two? It's well, molecular weight is the weight that it, so think of the molecular weight as a clue. Yeah, so the higher the molecular weight, the better. But it's really because the longer chain provides more spots to do other kinds of London dispersion forces. So if it's a short chain, there's only a limited place that it could do a dispersion force. Probably, there's really no place. But with this longer chain, you can do dispersion forces on the end of the chain. And the longer that chain is, the more likely it could do dispersion forces.
So molecular weight's almost completely.
It correlates with the London dispersion force increase, yes. Okay. All right, so let's switch slides. And we're going to see more evidence that the shape of the molecule, what it looks like, is going to affect the IMFs. So this length of the chain I keep mentioning as a way, instead of thinking of, yes, think of molecular weight, that's a good indicator. But it's really the shape that matters, and we'll see why. All right. So, just really quickly, what is the functional group and dominant interaction for each type of molecule? So this is like a good quiz question. What can you tell from these? Well, from the endings of the names, an A-N-E is an alkane. And from an alkane, you should know what an alkane looks like. You're not going to have to know the exact numbers of carbons, so bute is 4, hex is 6. But these are both alkanes, and so the only IMFs involved are going to be London dispersion forces. Acetone, pentanone, what does that tell us? Well, the O-N-E ending, that's a ketone. Ketones have this in them, which creates a dipole moment. So there's carbons on either side, of course. That's the ketone. That's the generic ketone. So this does dipole-dipole interactions. And then propanol, 1-pentanol. The OL ending, that's for an alcohol. And an alcohol has an OH in it with next to a carbon. Without this thing. So just the OH. That does hydrogen bonding. Okay? So the dominant interaction, hydrogen bonding, dipole-dipole, dispersion forces. So, and the boiling point would go up as you go down this list because you get stronger and stronger IMFs.
And you said that ketones have that carbon-oxygen double bond, right?
Yes. So the generic formula for a ketone, let me use the R thing. Remember, R means any length carbon chain. So it has to look like this for a ketone. The aldehyde is similar, but it has a hydrogen on one side. Carboxylic acids are similar, but it has an OH on one side. This is going to have way stronger IMFs than a ketone would, because you've got your dipole moment here, plus you've got your hydrogen bonding here. So this is pretty powerful, like in terms of IMFs.
If a molecule does hydrogen bonding, it can't also do dipole-dipole.
So if it's just the OH,
Mm-hmm.
I would say that it just does hydrogen bonding and dispersion forces.
Okay.
But if it's got an OH and it's got another part that has a different dipole, I would say it does all three. Yeah.
Okay. So like in that acid one,
Yeah.
so there's a dipole from the double bond and then
Uh-huh.
the hydrogen bonding between the OH.
Yep.
Okay.
Yep. Yeah.
And then for the pentanol, the NOL, the suffix, what grouping is that one for?
For alcohols, so OH groups. So yeah, go back to that list of things that was circled on one of the slides. It's just all the functional groups you're expected to know. Now between these two, and this is, I'm not going to test you, I think, on the, I'm not going to test you on the length of the chain, but prop means 3, pent means 5, acetone is only 3 carbons, pentanone is 5 carbons, bute is 4, hex is 6. If you saw a formula, you'd be able to tell that between two different things, the heavier one, the one with more carbons, is going to have the higher boiling point as well. Okay?
Why did you say acetone as far as you were counting them?
So acetone is the common name. It's got 3 carbons in it. It looks like this. Technically, it should be called propanone because it's got 3 carbons. Yeah. Yep.
So there's isopropyl alcohol
Mhm.
versus isopropanol.
They're the same thing.
Yeah. Okay.
Yeah, isopropanol is the. Yeah, they're both fine. There's so many names. So isopropyl is this. This is isopropanol. You could also call this 2-propanol because the OL is on, or the OH is on the second carbon of the chain. It's got a lot of names that you could use. It gets stupid sometimes. But if you take organic, that's what you're going to look forward to, nomenclature. It's like you're going to have to learn how to name these, like, you'll have to learn how to name that. And like you'll start, oh, what's the longest chain? And then I can number them, and then whereas the functional group, and then I have to do the side groups, and it's just a long, convoluted name. It's better than bio, where everything is a common name, and you have to just memorize everything. You'll see.
Biochemistry, is what you're saying?
I think, yeah, a little bit, yeah. Biochemistry, they do a lot of memorization too, but they are a little bit more systematic than biology. I know that the taxonomy of animals is systematic, but that's about it. That's all as far as I can tell. Anyway, this one is a little trickier, so let's try this one real quick. Which one so rank them, lowest to highest boiling point. And if you can't figure out one of them, just take a guess. We'll talk about why. So highest boiling point on the right side, lowest on the left side. Okay, everybody guessed, I think. So let's see what we think. Excellent. All right. Almost an even split between B and C, with one person voting A. So the actual answer is B. So, okay. I think it's pretty clear that everybody was focusing on the oxygens, that's good. But an OH does hydrogen bonding. The O in the middle here, so that you have to understand condensed structural formulas. This O is connected to a carbon and a carbon. So this H2 H is coming off the carbons. The main chain is C connected to O connected to H. That's an ether, which only does dipole-dipole forces. So 3 is stronger than 4. It has a higher boiling point than 4. Now, so the question is it B or C? It's B, but why is 1 higher in IMFs than 2? So if you went by molar mass, you might have guessed that 2 is a higher molar mass, higher IMFs. Because if you calculate the molar mass of this thing, 2 chlorines, chlorine is 35.5. It's about 71 grams per mole. This thing, 4 carbons, that's 48, 12 times 4, plus 10 hydrogens, 58. That's a lower molar mass. But you also might think, well, chlorine is 1 row down, so maybe more polarizable, slightly, than carbon is. Well, even then, you have to remember, so this is where we're going to learn shape plays a huge role in how strong your dispersion forces are going to be. This Cl2 molecule is a pretty small package. It's just 2 atoms bounded together. It's almost round. I mean, it's a little cylinder. It's pill-shaped, I guess, if you want to think of it. This thing is longer. It makes a chain of 4 carbon atoms. It's very cylindrical shaped. And this thing is basically exposing more surface area. There's more place. It's a bigger molecule. It's going to have more opportunity to do dispersion forces than this does. And so for that reason, this one has got a slightly higher boiling point. It's got slightly stronger dispersion forces than Cl2 does. Now, I'll give you a more clear version than on the quizzes and exams. This one's a little bit rough because it's kind of hard to tell. But that's how it works, and you can see with boiling points it's true. So that one's the highest. That one's next. Hydrogen bonding, dipole-dipole forces. These are both dispersion forces, but you can see that this one has a higher boiling point. So it has everything to do with the shape. It has everything to do with the surface area, how big the molecule can, how stretched out it is. And okay, so we'll see an example of why this is. FYI, this is fine if you need a flow chart to help you sort in your head how to decide what kind of IMFs it does. This is not too bad. This includes the ion dipole forces as well. So when you have a mixture of like water and salt, you have ions, and then you have a molecule that has dipole-dipole, technically hydrogen bonding, but the ions will interact with the dipole moment of water and do ion dipole forces, which are actually stronger than all the others. So if you need that, you can go over it like here. So here, this chart is including hydrogen bonding as a van der Waals force. The other chart didn't, so you can see that it's not consistent. So we're not going to worry about that. Don't worry about that at all. I'm not going to quiz you on van der Waals forces. I will quiz you on IMFs in general. Okay, so given what we know so far, which one of these do you think would stick together better? So not the molecules, but a strip of Velcro side by side, or a ball of Velcro touching like that? You can just say it if you want to. All right, I think everybody's on the right page. 2 strips of Velcro will stick so much better than those like Velcro tennis balls would, right? It's pretty strong still, but 2 strips of Velcro is even better. And so that's the idea behind how molecules would do interactions with each other with dispersion forces. A lengthy molecule like N-pentane, which is cylindrical shaped, would have more IMFs than the isomer, right? It's got the same formula, but it's connected differently. This one's more ball-shaped. And so the ball shape means it's going to have less ability to interact with its neighbor. So when they come into contact with each other, they can only interact at one point. Whereas these two cylinders, if coincidentally they interacted like that, of course they don't always do that, but when they do interact like that, there is a huge area over which they can interact. And so because of that, this has stronger IMFs. It's got a higher boiling point. That's lower. So shape is a huge factor in IMFs. There it is, same thing. Large area of interaction versus a smaller area of interaction. And we can prove it via other methods. I mean, if the boiling point wasn't enough, you can do computer simulations. So in 221, our last lab, we did electrostatic potential calculations. This is very similar with Spartan. And when you calculate what the dipole moment would be for any of these things, this one is small, 0.03, 0.04 dBi. This one is so small, it's practically 0. So it's 0.0000, it's like times 10 to the minus 7, right? So it's tiny. And in terms of the area, that one is slightly bigger. So there it is. There's the area. There's the dipole moment, and so that makes the boiling point slightly higher. Okay. So shape is a big deal. So besides dispersion forces, can shape affect other things? And yeah. So here we have two molecules. They both have an OH group on them, an alcohol. And we know that OH means this thing can now do hydrogen bonding. But do they do hydrogen bonding equally? These are actually isomers. They're both C4 H10 or H9OH. They're both that. But this thing is more accessible than this one. So this is where you got to start thinking a little bit more three-dimensionally. When another molecule wants to interact with this one and be attracted to this OH, it can come in from a lot of different directions. But this one, if another molecule of this kind wants to come and interact with this OH, first of all, the other molecule has to be oriented the right way, and it has to come in from a very specific angle. It's being blocked by other methyl groups from coming in at more oblique angles. So accessibility is another thing. And we call that in chemistry steric hindrance. So this has more steric hindrance than this one does. And because of that, I don't have the actual numbers. Because of that, this will have a higher boiling point. This will have stronger IMFs than this one does. Again, this is starting to, this is where organic gets a little bit tricky for people because you have to visualize everything. When they encourage you, if they don't require you to buy a model kit, I would heavily encourage you to buy it anyway. Having a model kit at home when you're building these for organic chemistry is a very good thing.
You said this one had the higher boiling point.
Yes, this one will have the higher boiling point because it's more accessible. That OH can be approached from lots of different directions by other versions of the same molecule, or water. All right, so similar question. Which one of these has the highest boiling point? Not too hard, right? We're looking at line drawings instead. Gotta get comfortable with those. Okay. So it's all about accessibility. Yeah, you guys that right? Good. Not too hard. So the way I would approach this in the future is if you start seeing some weird shapes you just can't process. If you see a functional group that is going to be the place where all of the interactions happen, look at the carbon connected to it and then just count how many other carbons are connected to that. So this carbon has one other carbon connected to it. All right, here's the OH. This is the carbon that's connected to. This carbon is connected to 1, 2 other carbons. Here's the OH. Here's the carbon it's connected to. This carbon is connected to 1, 2, 3 other carbons. So the more carbons that are surrounding that guess that rooted carbon, what the functional group is connected to, the more sterically hindered it is. So this T-butanol, this is actually a very common group that organic chemists will attach to molecules, a T-butyl group, to make it really bulky and to make it really inaccessible on one side if you needed to design a molecule that way. It's a very, very common thing to see. Yeah. Yeah.
Just checking, it's implied that hydrogens are attached to these carbons in the squiggly line drawings.
Yes.
Okay.
So every carbon should have 4 bonds, and if you don't see 4, then the other bonds are hydrogens.
Okay.
So this carbon here has already 4 bonds. So there's no hydrogen on this one. Yeah, so this one has 4, so no hydrogens here, but this has 3 hydrogens, that has 3 hydrogens. This has 3 total bonds, so it has 1 hydrogen that's not shown.
So that break is on purpose.
Yeah, I think it's PowerPoint drawing, so it's not super accurate. Yeah, it's you can draw the same thing like that.
Gotcha.
Same thing. It's not intentional. I think it's just.
Okay. Just never seen before, so I wanted to make sure.
Sorry. Yeah. Okay. If it was you feel free to ask if you see something like that and you're like, is that supposed to be there? Does that mean anything different? And I could tell you should know, or I'll say no, it doesn't mean anything. Okay. So space filling models are a little bit helpful when you want to see kind of the steric hindrance. I'm not sure that they're the best without having the ability to rotate it yourself. But here is the first one, the N-butanol, where there's a lot more accessibility to this OH group. A molecule of the same kind come in from a lot of different directions. This is the middle one. That's the very sterically hindered one. And you can see there's a carbon right in the center, and then there's these methyls that kind of bulk it out a little bit. And you can make this even worse. Like you could add more branches to make it really bulky. But yeah, this is a little bit less accessible, and so it's going to lower the boiling point a little bit. It's not going to have as strong of IMFs. Yeah. So, okay, what about this? Let's try this one real quick. Lowest to highest. Okay. So, we'll stop it there. Okay. We got a couple different votes. All right. Most people voted E, and it is E. So first, let's focus on like the thing that doesn't fit, and that is there's a bromine in there. That's unusual. So you might think, oh, it's more electronegative. I think if you look this up on the electronegativity table, it's not that electronegative. It's not super different from carbon. So really, it's more about polarizability than anything else. So even then, this is probably going to have the highest IMFs. It's a straight chain. It's got a more polarizable atom on the end. So it's going to have the strongest London dispersion forces. So that's the highest boiling point. This one is probably the lowest because it's just got 1 carbon. So that's the lowest. And as far as between these two, B and D, this is what makes it a little bit difficult. There's 5 carbons here. There's only 4 carbons here. But if we're going by shape, this is just a big round ball. You know, it's just big. It's not exactly spherical, but it's close. This is more cylindrical. So I would expect this to have a higher boiling point than that would. Not as good as this one, but higher than that one. And so this is the one that makes sense to me. So A is the highest, then B, then D, then C. again, I'll give you better, like the 4 carbons versus 5 is, I know that throws people, so I will endeavor to give you more obvious differences as long as you know the rules.
Would shape take precedence over weight to a certain extent?
It depends. Yeah, so, I mean, C60 is it's not a very good comparison, honestly. It's round, but it's humongous. It's definitely a solid. I don't know. That's not a good comparison. It really depends. So when we're going to give you, like I said, I'm going to give you very obvious examples
Okay.
where it's clear that shape will take precedence if the weights are the same. Yeah, I mean, I would look up stuff if I didn't know it. So this is just what is more obvious, basically. So let's talk about what, besides boiling point, can we get out of understanding IMFs. And so there's a couple properties that you may be familiar with, maybe not. I know people have heard of surface tension. Maybe not viscosity, but probably not capillary action unless you've taken some bio or biochem. So let's talk about surface tension first. What is surface tension? This is technically the energy required to increase the surface area of a liquid. And so basically, liquids want to have the minimum surface area possible because the larger they make their surface area, the more energy they need. If you ever look at what happens to a drop as it's falling with a high-speed camera, they will be completely spherical until they hit the ground. You can see tiny dewdrops. They still say completely spherical. So if we look at like some different surface tension values, there's water, ethanol, hexane. I think you can see a trend because we know that water is going to have very strong IMFs. It's got 2 OHs. Does double the hydrogen bonding. Ethanol does only one. It's only 1 OH. And then hexane doesn't have any hydrogen bonding. It's nonpolar. And so the surface tension values are going down. Yeah, that's all I can say. If you're curious about the unit for surface tension, that's kind of a definition of what it would mean. If I have some water and I wanted to increase the surface area by 1 meter squared, I would take 0.0729 joules to do it, which doesn't seem like much energy, but it's relevant. It's, that energy difference is enough for surface tension to matter. So another way to think about surface tension, let's think about it in terms of molecules, since that's what we care about. Liquids want to minimize the number of molecules at the surface. That's kind of what they're trying to do when you think about, well, what surface tension is. So let me show you another way to think about it. If you imagine water, a water molecule, and just imagine water as a sphere, just to make things simple. So here you have a water molecule, and if you think of the 3 cardinal directions, I guess, up, down, left, right, forward, and backwards, there could be water molecules in all of those directions doing attractions with that one water molecule that I just picked out at random. And so in terms of attractions, it's pretty balanced. It's being pulled in all directions equally. But if I look at a water molecule on the surface, backwards and forwards are balanced, left and right are balanced, but up and down are not balanced. There is a water molecule below it that is attracting it, pulling it downwards. There's nothing on top countering that. And so the tendency of every molecule on the surface is to be pulled into the center. And so that's where that's where the tendency of liquids wanting to minimize the number of molecules at the surface comes from. It comes from this imbalance of attractions. So the stronger the IMFs, the stronger those surface tension is going to be. And so that's where we get these water skippers and dewdrops because water has very high IMFs, and so it's going to have large surface tensions. You can balance a paperclip on a pool of water because the paperclip is light enough and the water molecules do not want to, like if I stick my finger in a puddle in a glass of water, what I'd be doing is I'd be increasing the surface area. So in addition to whatever surface area was already there, if I put my finger in, now there's this surface area of the water surrounding my finger. That's increasing the surface area. So for a little while, you can touch the surface of water and nothing will happen, assuming your finger's super dry and nothing else is on it. But eventually you'll break through. And that's what's happening with the water skipper. There's not enough pressure from its feet to pierce that surface tension. So they're just standing on water. And it turns out water has the highest surface tension of any liquid except for mercury. Any ideas why mercury is higher? So mercury is a liquid, right? What do you think, anybody?
It's heavier?
Mm, somewhat related. But what is mercury?
It's metal.
It's a metal. What do metals do? What kind of bonding do metals do? Metal bonding, right? So metal bonding is stronger than IMFs, right? It's not as good as ionic bonding and covalent bonding, but two mercury atoms in liquid form are still going to do metal bonding, and that is a much stronger force. And so the surface tension for mercury is even greater, and that's what makes mercury so much fun to play with. Because if you pour it on the bench top, it'll make all these little bees that just roll around. It's very toxic. The act of playing with it on your hand is not that bad. The problem is everything creates vapors, and when you breathe in mercury vapors, that's the bad part. So, yeah.
There was a story about a chemist who was studying mercury.
Uh-huh.
And they were using a different, it was a different kind of mercury.
Yes, it was a mercury compound, probably.
Yes.
Something connected to, like, it was a mercury in an organic compound, like a methyl mercury, I think it was.
And so it was really toxic, but she didn't know. And
Yeah.
she was very careful, but I guess when she took her gloves off, a little bit of it might have gotten on her or something.
Mm.
She had all these terrible problems, ended up dying, horrible
Yep.
death.
Yep.
It was really hard to
Mer-
listen to.
Mercury is weird. So pure mercury, metallic mercury, is it interferes with the nervous system. I know that, but it only can get inside you if you swallow it or if you breathe it. It doesn't go through your skin or anything like that. But when you make a compound out of it, that's a different story, and it's way more toxic that way. But a lot of things are like that. Sodium metal is explosive, but it's required in our diet as an ion, right? So different forms will be very, very different. Yeah, that story that you told, that they tell that to all chemists who are working in labs because I think in that case it actually went through the gloves.
Okay.
I think that compound, the nitrile gloves are not good enough for that some compounds. We would never work with that in this lab, don't worry. Yeah, they tell us that. Just so you have to be careful. But like people who have mercury fillings, they used to do fillings made out of mercury amalgam. So mercury mixed with silver, I think. I can't remember what metal. And it makes a really hard alloy, which is why they used it. Those are fairly safe. Like it will not leach out of your mouth. And they're fairly safe. What's dangerous is when they take them out, because to take them out, they got to drill them out, and they create all this dust, and that's when it gets into your body. So if you're an older person, they don't do that anymore, and you have mercury fillings, leave them alone, unless they fall out on their own. Yeah, then it's fine. So I'm not going to turn the clicker on for this because this is pretty obvious, but. The idea is if you see a series of compounds and the surface tension is increasing, then we can deduce that the intermolecular forces within those compounds are increasing as well. Okay. So surface tension, that's another way to judge IMFs. Here's some more numbers. And here's mercury's, 48. And they're all times 10 to the minus 2, so you can compare 48 versus 7.3 for water. So, yeah, mercury is super tight. Like it makes a very, very tight surface. Now, that does not mean you can't react stuff with it. This is a physical property. So if it's going to react with mercury or react with water, that's a different story. But yeah, this trend follows the IMFs that we understand. So hydrogen bonding, hydrogen bonding, hydrogen bonding, but just shorter chain, just dipole forces, dipole moment, I mean. Okay, viscosity. This is another one that we can relate directly to IMFs. Viscosity is resistance to flow, and it's got a weird unit. It's poise. You don't have to worry about the unit, but it's grams per centimeter per second. And to imagine what viscosity is, just take an inclined slope, take your liquid, and pour it down the slope. And viscosity is a measure of how fast that liquid moves down the slope. So honey would crawl down the slope. Water would go pretty fast. Honey is more viscous. That's viscosity. And that's the same idea, if you could imagine it. The higher the molecular weights, I didn't mean to show that. The higher the molecular weights, the higher the viscosity. Sorry, the higher the intermolecular forces, the higher the viscosity. So the heavier that substance is, the more weight it has, the more IMFs it has, and so the more viscous it's going to be. So very at the beginning, when we looked at the table that had the hydrocarbons, gasoline, which has 8 carbons in general in the compound, it's pretty viscous. I don't know if anybody's played with gasoline. It's very liquidy. Diesel is thicker. When you get kerosene is a lot thicker. When you get to 38, 40 carbons, that's when you get to asphalt, which is not even a liquid anymore. It's more tar-like, solid. So more viscous, yeah.
So something like weird slime things that you buy at stores nowadays.
Uh-huh.
That, I mean, I guess my first question is, are those carbon chains? And my second question is, are they long and
All right.
have a lot of IMFs?
I can show you the slime that you buy. It's not exactly the same as what we're talking about, but it's similar. I can't remember the formula for glue, but glue is a polymer. It is a chain, a really long carbon chain, and I forgot what the branches are on it. That's what I'm trying to remember. I believe it has like some oxygens on it and stuff, OHs or something like that. So think of, and this, I don't know what it is exactly, but think of a long carbon chain. So this is one of those super long carbon chains. And every other carbon, there's going to be maybe an OH or something like that. I'm making this up. I don't know exactly what glue is right now, but
C4H6O2.
O2.
To the end.
So there's 2 sets of OHs. Anyway, something similar to this. And just imagine this chain is like 1,000 carbons long. That's how long, like more than that even. That's how long the polymers are. Glue is. And it's got OHs intervally spaced. So already you can see that, hey, strong IMFs. That's why glue is really thick and viscous. It doesn't explain why it dries and needs glue, but that's a different story. So when you make slime, imagine you've got a bunch of these chains with OHs. And when you add activator, and I hate that word, what that is a borax solution. And borax is a compound that is made of boron. And I think it's something like B with, I don't know exactly. It's probably 2 borons, but it's something like that, something like it. And what this does is it comes in and it makes weak bonds between something like that. And what it does is it cross-links polymers. So that's the same process as when you take rubber and you vulcanize it. So you heat it with sulfur and it makes the rubber a lot stronger. You're cross-linking these polymer chains. This is plastic stuff.
Yeah.
So that's what slime is. You're basically doing these weak bonds between the chains, and now it's got slime-like consistency. Yeah.
That's cool. That makes it sticky as well. So like when you touch it with your finger.
Well, it was already sticky as a glue.
No, I suppose
And I imagine that the stickiness is related to the hydrogen bonding. Yeah, I don't remember exactly. I don't know enough about the chemistry in detail, but a little bit related to this, but not exactly.
Yeah.
Okay. So viscosity, the other thing that we know about viscosity is that when we change the temperature of a substance, it gets less viscous. So honey, when it's cold, it's really thick and it's hard to flow. If you heat it up, it pours like water. It does. And the same happens with everything else. So most things, as you increase the temperature, the viscosity will decrease. So if you think about why that would happen, your temperature is the higher the temperature, the more kinetic energy these molecules will have. And so this is where it comes back to what you were thinking. The higher the temperature, the faster they're moving, the more energy they have. They can break those IMFs more easily. And so the less viscous it's going to be. So again, if you compare substances that have different viscosities, the higher viscosity substance should have higher IMFs. Okay, and here's more. So these are the hydrocarbons, pentane through nonane, 5, 6, 7, 8, and 9 carbons long, and the viscosity is increasing significantly. Okay. I won't turn this on because we're running out of time, but this is exactly the same question as we saw before, but instead of asking which has the higher boiling point, this is asking which is the highest viscosity. It's exactly the same question. We're looking for the one with the strongest IMFs. All right, strongest IMFs gives you higher boiling point, gives you higher viscosity, gives you higher surface tension. All right, they all relate back to IMFs. Now, last but not least, capillary action. This is a weird one. And this is talking about the attraction a molecule has with a glass surface. So to understand this, we need to think about, well, what does a glass surface look like? So glass, there's lots of different formulas for glass, but generally glass is silicon dioxide. And if you look at the surface of glass, the exposed part is a bunch of oxygens. And these are usually oxygen anions in that case. So glass surfaces have a large negative charge on them. Okay? So if they've got a large negative charge, something that is polar would probably be attracted to that. Right? The partial positive side of water is going to be attracted to that negative charge on the glass surface. And that's where the meniscus comes from. When you pour something into a graduated cylinder and it makes that curved surface, it's the water attracted to the glass. It's climbing up the glass walls because it loves to be near that glass wall. And so that's why it makes that curved surface. So there it is. There's a meniscus inside a graduated cylinder. If you do the same thing with mercury, though, mercury does not make a concave surface. It doesn't make a meniscus that looks like this. It does exactly the opposite. It makes a convex surface. It domes. And so to think about why that happens, let's talk about the difference between the attraction water might have for itself. We'll call that a cohesive force. So water attracts water, right? Hydrogen bonding. But water is also attracted to the glass. We call that an adhesive force. And in water's case, the adhesive forces are actually stronger than the cohesive forces. And so water will climb up the glass walls because it likes the glass walls better than it likes other water molecules. But for mercury, the opposite happens. The cohesive forces, mercury to mercury, is much stronger. It's a metal-metal bond. And it's not as strong as the attraction to a glass surface. And so mercury is not going to be attracted to the glass surface. So why is it domed? Any guesses? Smaller surface area, cohesive forces, but yeah, it's the surface tension. Surface tension. It's trying to make, the smallest surface area. And so that's the round shape. It makes that dome shape. Yeah, so it has to do with the relative strength of those intermolecular forces. So something like pentane. Pentane is a hydrocarbon, 5-carbon chain, non-polar. So the only forces it has going for are London dispersion forces. What would you expect to see if you poured pentane into here? Would you expect to see a meniscus as large as water? Probably not. You might see a meniscus still because there's still going to be London dispersion forces involved, but the meniscus might not be as large. It might be a little smaller. Yeah.
Just curious, if you put the tube of mercury in it under vacuum, would it make like a higher dome?
It shouldn't.
I mean, arguably flat would have a smaller surface area, wouldn't it?
Yes. But hold on, there's a reason why. Hold on, let me think of it. It's still, yeah, I guess it is. But if you took away the glass walls, like it's still, the tendency is to make a sphere. Yeah, I don't know how to argue against what you said, and have it make sense. So yes, you're right. But if you made it flat, then you would have more surface area exposed to the glass surface. And so you'd still have those boundary conditions where you'd have nothing on the outside pulling. It would all still be internal. So yeah, it's not like the glass is helping. It's just another boundary, and it still wants to be round. So it's partly gravity too that you have to compete against, but that's why it's not making a big giant ball inside there. But yeah, it's still the dome. It's still going to make a dome. It's still lower energy. Okay. So there's so much more that you can do with intermolecular forces. If you've ever done anything with your car's windshield and used Rain-X, you're basically messing around with the intermolecular forces on your windshield so that water doesn't stick to it, right? It beads up and flies off. These are just basically commercials, but Magic Sand, this is a silicon with 3 methyl groups and an OH on it. It's not regular sand. It's a special compound. And this stuff has such strong intermolecular forces that it only wants to interact with itself. And so if you take the sand and you pour it into water, it does not want to interact with water at all. So it does this weird clumping, and then when you take it out, it's completely dry. So this is all messing around with IMFs. You're designing molecules that have these interesting, strong IMFs. Yeah, it's repelling water because it would rather interact with itself, basically. What's that?
Is cat litter in this? Does it absorb water? Cat litter?
Oh, well, that's different. So cat litter is very porous stuff. It's got a lot of little cavities that are built in that absorb smells. Yeah, it's some kind of clay material. Yeah, and this is another commercial, but this is similar to what Rain-X does. And this is gonna be another commercial one in front of the commercial.
What if you could get rid of your kitchen
Come
garbage
on.
at the push of a button? Hey, I'm Matt from Pila, and I want to introduce you
You
to
know
my
what's
friend
weird?
Mo. At Pila, we're
I have never searched for this on my phone. I have never searched for this on my computer. My wife talked about this.
Oh my
and
gosh.
they're listening.
Yeah.
Oh my God, this is creepy.
True, actually, the OK Google people, they do listen.
Yeah, it is scary. So this is like you're spraying this material on any surface. You let it dry, and it has a coating now that is super hydrophobic. Yeah, so one side is coated. I mean, look, there's flaws with this stuff. Like, it probably doesn't last long after we apply it. It leaves everything a little bit whitish, so you may not want that. I don't know. Who knows how long it lasts? It may degrade with sunlight. Who knows what flaws it has? That resistant water. Oh, the resistant gases. Yeah. That's a neat test. No water. Anyway, just a commercial. But yeah, this is all IMFs. So IMFs are fun to play around with. Designer molecules is where it's at. All right. If you have a problem with your exam,